All right, so we've just gone over the exam. Your next assignment is due on Wednesday, March 2nd. So we've still got some time for that. We're going to be talking about unit hydrographs today. So let's get into that. A unit hydrograph is one of the simplest ways to predict what flow is going to come out of a watershed. And there's a couple of different ways to obtain a unit hydrograph, but the idea is that you measure what is the response out of a watershed when there's 1 unit of rainfall excess. So let's say, for instance, that a given watershed that we're familiar with, we know that if there is 2 inches of rain, that 1 inch of that 2 inches would be lost to surface wetting, would be lost to infiltration, would be lost to interception, and then that would leave 1 inch of rainfall excess. So with that 1 inch of rainfall excess, what we would do is we would measure what does the hydrograph look like for this particular watershed with 1 inch of rainfall excess. So if we had that 1 inch of rainfall excess and it was distributed during a 1-hour time period, then what we could do is we could put a pulse of rainfall into the watershed and then just measure what comes out of it over time. You can see that this is being represented by, here's our Rainfall Hytograph, and it's showing a depth of 1 inch of rainfall excess, and they're calling it here effective rainfall. And it doesn't matter if it's 1 inch, a centimeter, a millimeter, it's just a certain known amount of rainfall excess. And once you know the response of the watershed to 1 inch that falls during a 1-hour period, then you can translate that understanding of the relationship between rainfall and runoff to other time periods and to different amounts of rainfall excess. So if you know what the watershed's going to do to a 1-inch storm, then you can see what it would do to a 2-inch storm would be effectively double it, according to the unit hydrograph approach. You'd just peak it up by twice as much if you had twice as much rainfall excess. There's a couple of assumptions behind this idea, and the first is that the rainfall intensity is constant. And so you can see that this rainfall hydrograph is flat, and it's just assuming that during the entirety of the rainstorm, the amount is constant. And if that's not true, then what you'd have to do is break it up into periods. So if you have a rainfall hydrograph that was built using 1 hour of rainfall excess, then what you could do is you could break up your storm into 1-hour increments. And we have an example here in a moment that does that very thing, where we're going to be taking a given unit hydrograph and then applying it to a longer storm. It assumes that the water falls everywhere in the watershed with uniform distribution. So it assumes that it's raining the same everywhere. It assumes that if you observed the storm to generate your runoff hydrograph was 1 hour, then it assumes that the storm that you're going to have also follows that same 1-hour time increment. And then when that's not true, you have to make adjustments in order to apply this approach to different situations. And it also assumes that the watershed isn't changing. And of course, remember I told you that during the spring versus during the summer, the watershed performance may be completely different because now the trees are all leafed out and so on. So you just have to be aware that if you generated a unit hydrograph during the winter time, that how the watershed behaves in the summer may be different. So you perhaps need to have a unit hydrograph that represents the conditions that apply when you're actually wanting to run your simulation. So these are the assumptions. Now, to see how we apply a unit hydrograph to the real world, consider that we have some watershed. So this outside perimeter, do you remember what would define the outside boundaries of a watershed? It's a ridgeline. It's a high point in elevation, and you can see that this thick blue line here just represents streams, And so water's flowing over the land until it gets into a stream. Then it flows through the stream towards the outlet. So here, where the cursor is, let me make it red. Here is the outlet of our watershed. All of the water in this entire watershed is going to end up at this point. It concentrates to that location. Now, I've defined a few boundaries, and these dashed lines break up the watershed into zones where it takes a certain amount of time to get to the outlet. So this zone 1, all of the area within this region will get to the outlet within the first hour. That's what the 1 means. It's the contributing area during the first hour of the storm. After 2 hours, then this region is now contributing to the flow at the outlet. So if you had a storm that was it began and it kept going for, let's say, 24 hours. The first hour at this outlet, you're only getting water that fell in region 1. At the end of the second hour, now this entire region 2 and region 1 is contributing at the end of the second hour, and so on and so forth. So it would take 6 hours before the entire watershed is contributing to flow at the outlet. So these are just different regions that have been defined by how long it takes for the flow to contribute. And of course, in the real world, if we had the shape looking like this, the boundary lines probably wouldn't be horizontal like this. I've done that just to simplify the representation. You know, like the actual time boundaries would be curved to match the geographic features within the watershed. So like probably it would match some of the interior ridge lines and not just be horizontal like I'm showing here. But the main idea is you can see what amount of the area in the watershed will be contributing within a certain period of time. So let's say that I have a storm that provides 1 inch of rainfall excess. And remember, I'm not saying 1 inch of rainfall, I'm saying 1 inch of rainfall excess. So that means that there was also a little bit more water that satisfied all of the abstractions, like infiltration, surface wetting, ponding, interception, and so on. So we've accomplished the abstractions. There's still additional leftover water. So 1 inch of rainfall excess, if it fell everywhere on this watershed during a 1 hour time period, then this is the runoff hydrograph that we would see at the outlet. So here at the outlet, at the end of the first hour, the flow rate would be 10 CFS. Then at the end of the second hour, it would be 100 CFS. So you can see so on and so forth what would happen. But remember, it was only raining from time 0 until time 1. So this was a 1 hour storm, and it's just taking a long time for the water to drain out of the watershed. So, you know, this 6, the water fell on the land and it took 6 hours to make its way to the outlet. That's by definition how we defined this region of the watershed. So here's the runoff. And what we could do is we could say that the unit flow for time 1 is 10 CFS. So that just means that we know that this was caused by 1 inch of rainfall excess. And so if we had a different amount, we could just scale up or down how much we expect to see at the outlet. So this is for 1 inch. If there was 2 inches of rainfall excess, then our hydrograph would be 20, 200, 400, 300. It would just be double. So that's the approach. So let's say, for example, what if instead of just 1 inch of rain that falls over the period of an hour, what if we had a storm that was during the first hour it was a 1/2 inch of precipitation, and then there was 1 inch, and then 1.5 inches, and then half again, but that was broken up over 4 hours. We're going to go through the process of using the unit hydrograph to predict what the runoff looks like. And it's most easily accomplished using Excel. but you can do it by hand. But this is something that Excel handles really nicely. So I'm going to show you how to do it with Excel. And when we do, we're going to have a given precipitation amount for a certain period. And so P is this. So P1 is ½ an inch, P2 is an inch, P3 is 1.5 inches. In this formula, U is the unit runoff. So U would be U1 is 10 CFS per inch of rainfall excess. So the units of U is CFS per inch of rainfall excess. So we'll have a hydrograph that at any given time has a precipitation amount multiplied by the unit hydrograph that corresponds to what area is contributing up at that point. So there's going to be multiple pulses of rainfall, and we're going to combine together the runoff hydrograph. This is kind of an abstract figure that I think will make more sense to you when we actually open up Excel and start applying the process. So let's do this. Let's use this unit hydrograph, and this is our precipitation, but remember, it's the rainfall excess that we have to be aware of. So let's assume that there are abstractions of 0.3 inches per hour. Okay, so let me just start up Excel, and we'll go through this together. All right, so here is the unit hydrograph. Let me put some titles on here. So it's hour, and then unit U, and this has units of CFS per inch of rainfall excess. Okay, and what we're going to see is we want to have something that's a time column in hours, and then we'll put in the rainfall amounts here. Let me just 0.5, 1, 1.5, and 0.5. Okay, so 0.5, 1, 1.5, and 0.5. So this precipitation amount was in inches. And then we should also have a separate row that is our rainfall excess. I'm just going to label that RE, rainfall excess, inches. So the problem said that there's 0.3 inches per hour of abstraction. So if we're losing 0.3 inches per hour, then that means there's only going to be this minus 0.3. So there's 0.2 inches left over during the first hour. Then during the second hour, it'll be 0.7 and 1.2 and 0.2. So everybody understand what the differentiation here between the precipitation and the rainfall excess is? All right. So during the first hour, it's just this rainfall excess that applies. And so the flow rate that we see is this amount times that. So 2 CFS. And I guess I should have here Q in terms of CFS. Now let's just follow this first pulse of rainfall through the watershed. Okay, so that 0.2 inches, first it was only applying to this close part of the watershed. And then we can, let me anchor the reference to the precipitation amount and then drag it down through the rest of the hours. Okay, so it's basically a fifth of the rainfall unit hydrograph. So this is how much flow we would get from just this 0.2 inches of rainfall excess. Okay, now let's consider what happens in the next hour. So in the next hour, we've got 0.7. So it's going to be a similar thing, but it's delayed by an hour. So it's actually starting here. So it's 0.7 inches of rainfall excess, and then multiply that by the unit hydrograph. So 7 CFS, oops, let me drag it down. But I've delayed it by an hour because during the first hour, this 0.7 of an inch of rainfall excess doesn't have any effect because it hasn't fallen yet. So we just put 0 because that's the contributing effect of the second hour of rain during the first hour. So it's 0 because it hasn't happened yet, and then you just basically stagger the effect by an hour. And then we'll do the same thing for this next 1.2 inches of rainfall excess. And so I'm going to put a 0 and a 0 because during hour 1 and hour 2 nothing happens from this rainfall excess. But we start to see the effect in the third hour. So it's going to be the 1.2 inches of rainfall excess multiplied by the unit hydrograph. And I can drag that effect down through. And I guess what I ought to do here is extend our time a bit further. Okay, and then lastly, I'm going to put 0, 0, 0 because during the first, second, and third hour, this rain hasn't had any effect yet. It's not until the fourth hour that this 0.2 of an inch of rainfall excess has any effect. So then multiply that amount by the unit hydrograph, drag it down. Okay, so it's been 4 different pulses of rainfall. There was the first hour when there was 0.5 inch, subtract out the 0.3 of an inch of abstractions, so there was this amount of excess during each pulse, and then combined, it is the sum of all of these that are to the left. So the overall runoff that's coming out of the watershed is going to look like this. Now we've just gone through the spreadsheet solution that basically is described by this formula. This formula is kind of a conceptual illustration of, in any given hour, it's a certain hour's precipitation and a certain unit hydrograph that's contributing. So for example, in hour 2, it's P1 times U2 and P2 times U1. Now let's see if that matches up. In the second hour, it was this, which is P1 times U2, and this, which is P2 times U1. And then, like in the third hour, we start to see the third pulse of rainfall kick in, and so on and so forth. So this is the overall hydrograph of what we would predict to see if all of these assumptions hold true. So the assumptions being it's a constant intensity during the hour period, that the rainfall is everywhere in the watershed, it's not variable within the watershed, that we're doing this in 1 hour increments, which we did, and that the watershed is the same now when it's experiencing this series of pulses. The watershed itself is the same as when we generated the unit hydrograph. Okay, so you can make a unit hydrograph through observation. You know, like if I had a storm, if I had a rain gauge and a river sensor in a watershed, I could just wait until there was a storm that came along that met the criteria of an inch of rainfall excess during a 1 hour time period. But I may have to wait a long time, so there's also ways to synthesize a unit hydrograph. Any questions about this procedure for the unit hydrograph? All right, but sometimes you can't actually physically go out into the field and make the measurements you need to create your own unit hydrograph, and you have to synthesize one. So a synthetic unit hydrograph uses data that's gathered for similar watersheds, and you're kind of extrapolating into the place that you're interested in using the physical characteristics that were determined in other locations. So synthetic hydrographs just use like geometric data and statistical procedures to come up with a unit hydrograph when you don't actually have the real data. And one of the methods is called Snyder's synthetic unit hydrograph. And what it assumes is a triangular flow distribution. And we saw that before with the rational method, is just that the flow goes up to some peak. But in the Snyder's method, instead of assuming that the increasing and decreasing legs are the same length, here it says that it'll take twice as long for the watershed to drain as it does for the peak to rise up to its highest flow rate. I have a handout I'm going to give you that steps you through the Snyder synthetic unit hydrograph process. It's kind of a little bit of an abstract process, so let me give you this handout. All right. Okay. So the type of data that you need to be able to use Snyder's synthetic unit hydrograph is the area of the watershed, the length of the main channel, a shape descriptor, which is how long is it from the outlet, meaning where all the water drains to the centroid, the center of area of the watershed. So here in this illustration I said, let's just say that it's 2 miles, for example. And then these regional calibration parameters would come from having studied other watersheds in the same area and having a real calibrated hydrograph. So for our purposes it's given, but it was derived in another location that had similar slope, that had similar topography, vegetation, and so on, experiencing similar storms. So that's what these C-value parameters. And what we have to do is go through the process to ultimately predict what does the hydrograph look like. Like the hydrograph itself is going to be how much flow rate, CFS, you get from an inch of rainfall excess. So we want to know how high is this peak, and also how long does it take. The T sub P is the time from when the storm begins to when the peak itself is observed. So those are the two main things. Like this is a triangle here, and we want to know mainly what is the peak flow rate per inch of rainfall excess and how long until it arrives. Of secondary importance to us is the overall length of this base. So T sub B, it's good to know, but if we're just talking about sizing infrastructure and how big does the pipe need to be, that's mainly dictated by the time to peak and the peak flow rate. Since it is 12:46 and we don't have a lot of time, I'm going to bring the solution up on the screen just so that you know it's in the recording, but then I'll email it to you because it's just kind of a tedious process of plug and chug to get the answer. Let me show you what those calculations would look like. Okay, so you can see in the handout I've given you there's step-by-step methods. So step 0 is just gathering all these constants and the input data. Step 1, calculate the time to peak and the standard duration. And so the important thing here is to pay special attention to the units. And in the handout I've told you what the units need to be for each of these empirical equations that you're using. So you can see, for example, the standard storm duration here is 0.7 hours. the standard time to peak, 3.853 hours. Then you transform that in step 2 to find the time to peak for the desired storm duration, because you may have the standard storm duration of 7/10 of an hour, but you want to know what does the water shed during a storm that lasts a different amount of time. So you have to change the time to peak with this next step, step 2. So now we have a T sub PR for that. Then we're finding out how tall is the peak, and Q sub PR, when you go through the process, will give you in traditional British gravitational units CFS per inch, and that's inch of rainfall excess. And so that would just say that if you have 1 inch of rainfall excess that occurs during a 1-hour period, then the peak flow rate that's coming out of this watershed that has a 5-mile square length is going to be 551.9 CFS per inch of rainfall excess. So that gives you the height of the hydrograph. But now if we wanted to find the width of it, the step 4 is just finding out what the shape of it looks like here, the W75 and the W50. Since it's a linear distribution, I'm frankly not sure why they bother calculating both of those. But let's say that we do, and find the width of both of those, and then from that you can determine how wide the overall hydrograph is. So I'll email you this so that you've got the solution. And the second part of it was just, in this example, the first storm that we were interested in had a 1-hour duration. But the nice thing about this synthetic approach is that not every storm is going to last 1 hour. And so you can change the hydrograph that you determine by the Snyder's method to match a different storm duration. So if you had a storm of just 30 minutes, you can find out what the peak is going to be, how that would change. And in this example, the peak for the other storm, it was previously 551 CFS per inch. If you have a shorter duration, it takes the peak higher because it's the same amount of rainfall excess, but just occurring over a shorter amount of time. So higher peak, but it also changes the time to peak and so on. So I'll email you these so that you've got them on hand. I believe that you need to use the Snyder method on the homework assignment. So you'll just have an example of how to plug those numbers into a similar problem. Remember that the next homework assignment that you've got is going to be due on Wednesday, March 2nd. That is Wednesday of next week. So have a great weekend. I will see you on Monday.